We have a last talk on a deep factorization of style and structure in fonts. Oh, it's
all right, hi. So my name is Akshay. Are we off again? So yeah, today, time allowing, I'm going to be talking about our work on a deep factorization of style and structure in fonts. So I want to start by just briefly describing this task of font reconstruction that we'll be looking at. So suppose that we're given a small number of characters in a font that we've never seen before, or a font that this computer has seen before apparently. What we want to be able to do is reconstruct the remaining characters that we did not observe in a way that respects the style of those original observations. I really hope the other fonts will work. So this is what our data looks like. Essentially, we have this gigantic matrix where each column corresponds to a particular font, and each row represents a particular letter. And in total, we're going to have about 10,000 columns in our matrix for each of our data points, and we'll have 26 rows for each of the capital English letters. So there's been some prior work on approaching this reconstruction task, some of which has relied on generative adversarial models, and others which have used deep generative techniques, but neither of these really make use of this kind of inherent alignment that we see in our glyphs in this matrix format. So that's what we're going to do here, is we're specifically going to cast this problem as one of deep matrix factorization. And so what I mean by that is essentially we're going to assign an embedding for each column that represents the style of that font, and then we're also going to have an embedding for each row that represents the underlying shape of that character underneath the font. And each observation is going to be basically defined by the pairwise combination of some particular font with some particular character. And so at test time, we can think of the reconstruction task as essentially us being given a column that we've never seen before, and then having to infer what the style representation for that column should be. And then if we take that inferred representation and combine it with the character representations for the missing glyphs, we should be able to fill in those missing entries. And so we can think of this as kind of a form of matrix completion that we're doing here. So I want to kind of motivate this notion of disentanglement by previewing some actual output from our system. So in this case, we have some glyph. It's a P that's in this sort of bold sans serif font, and we want to be able to make changes to the style representation in a way that doesn't actually affect the underlying character form. So here we were able to add some serifs to that, but you still recognize it as the letter P. Conversely, if we were to switch it out for the representation for a letter O, which does not exhibit serifs in any font, we should be able to get exactly the same output regardless of whether our font embedding is telling us that we should have serifs or not. So there's some kind of complex nonlinear interactions that are going on here that we need to be able to capture. So now I'm going to get into a little bit about how our model actually works. So as far as the various components go, we've got our observations. These are going to be images of glyphs, 64 by 64 pixel images. And for each column, we're going to have a embedding for the font. And that's actually going to be a latent variable here. This is specifically going to be drawn from a multivariate Gaussian distribution that we'll have as our prior. And then we're also going to have an embedding parameter that tells us what this character is generally shaped like, irrespective of the style that it's rendered in. And we're going to assume that we have like some fixed number of these embedding parameters, one for each of those 26 letters. And additional columns in our matrix are basically going to be represented as further draws from that Gaussian prior, where again, we just have a deep generative process that's going to put that style together with the character embedding in order to render out the glyphs that we actually see. So one thing that you might notice here is we're also going to have some missing entries in this matrix. So in general, not every font is actually going to support every character. There could be special symbols that didn't get rendered, and so our model simply does not generate those missing entries. So now I'm going to talk a little bit about what this decoder actually looks like. So we need a way to take in a font embedding and a character embedding and produce a distribution on output glyphs. Specifically, we're going to parameterize this using a Transpose Convolutional Network. This is something that's seen good results in image generation through GANs and VAEs and other such work. To remind people what a transpose convolution is, it's basically a standard convolution that you're going to apply on an undecimated input, which basically means that you take the pixels and you pull them apart and insert zero padding in the spaces in between. So that kind of functions as a form of upscaling so that at the lower layers in our network, we're going to have very coarse, low-resolution representations that don't have a lot of stylistic features, and as we go farther down our generative process, we'll start getting more of that finer detail in. And in order to add in a bit more inductive bias into our decoder, we can actually go one step further, where now, instead of having the filters of those convolutions be parameters that we learn, rather, we're going to have a secondary network that will dynamically generate those filters based on the style representation. And the intuition for doing this is that we're sort of thinking of the character embedding as giving us some very coarse, low-resolution, kind of rough shape that's gradually getting hit with these filters that are adding stylistic properties of the font to it. So now I want to just kind of briefly take stock of what we've established so far and what our model really looks like. So we have some observations, we have these glyphs that we're generating, and then we have these latent variables, which are the embeddings for the particular font styles. And the parameters of our model are going to be the character embeddings for each row, as well as the parameters of that transpose convolutional architecture that I just described. And what we'd like to do now is really train our model in order to optimize the marginal likelihood of those observed glyphs where we sum out those latent variables. But unfortunately, we can't actually do this. And the reason is that the posterior over those latent variables given the observed glyphs is intractable in this case. And that's because these are these high-dimensional, continuous valued vectors which are getting passed through this complex, nonlinear decoder that we can't really go backwards through. So instead, we're going to approximate that posterior using an inference network. And that's going to allow us to form a variational lower bound called elbow on that true marginal likelihood that we want to optimize. And this is going to be another neural network with its own set of parameters, and we're going to train this inference network alongside the parameters of our real model over the course of training in sort of a strategy similar to what you may be familiar with from VAEs. And we'll also see that having an inference network is something that's going to be extremely handy for us at test time when we're shown a column we haven't seen before. So now I want to dive in a little bit into what the inference network actually looks like. So what do we need this inference network to do? Well, we essentially need to eat up an entire column of our matrix, and then based on that, approximate the posterior on the style representation for that font. And during training, we're going to be dropping out some of the entries from that column, and this is in order to kind of get our training time set up to better match what we'll be seeing at test time, where the network needs to be able to take in a potentially variable number of inputs. So we can pass these through some convolutional layers, and that can extract some stylistic features for each of the glyphs, but now we need a way to actually pull them down in order to get just a single representation for the entire column. I want to briefly return to the example we looked at previously with the serif P and O. And one thing you might note is that in this case at least, you would see serifs on the P, but you might not detect them on the O, because O's never have serifs on them. And so we need our pooling process to make sure that it preserves that information and is conscious of the fact that there are some stylistic properties that appear on some letters but not others. And rather we want to take the union of that information instead of just averaging it out. So our solution for that is to use a simple element-wise max. And once we have that representation for the entire font, we can then pass it through some further layers in order to get our parameters for our approximate posterior. So now I want to kind of back up a little bit and just describe how this inference network fits into our broader training process. So as I'd mentioned, we want to form our elbow on the marginal likelihood of our observations, and that lower bound is basically going to take the form of a difference between two terms, one of which is the KL divergence between our approximate posterior and the model's true prior, and the other which is going to be a reconstruction term. So to get the KL divergence, that's pretty easy once we have parameters for our approximate posterior. We can just compare that to the unit Gaussian, And in order to get the reconstruction term, we just draw a sample from that, pass it through our decoder, and then we can get some parameters which we can use to evaluate the probability of the glyphs that we saw. As a brief aside, I want to mention that we're not actually measuring that final probability, that reconstruction in the raw pixel space. Instead, we're actually going to be first transforming those glyphs into sort of a frequency domain using what's called a discrete cosine transform. And this is basically going to allow us to get kind of sharper, more realistic results without having to resort to something like a GAN. And you can read more about it in either our related work or the paper itself. So now that we have our reconstruction term in the KL, we just take their difference. This is our lower bound on likelihood, and it's what we'll be taking gradient steps on to optimize during training. So now that we've described the model and how we train it, we're kind of ready to get into some experimental results. But before we do that, I want to briefly describe the baselines that we'll be using here. The first one is going to be GlyphNet. That's the GAN that I had mentioned earlier. And then the other is going to be a simple nearest neighbors baseline, where here it's going to reconstruct fonts by just finding the next closest example by L2 that it saw in the training data. We're not going to be able to compare against the SVG fonts that I mentioned earlier, because that works on vectorized representations while we're in the pixel domain, and it also doesn't have a great way to handle multiple observations for the same font. So now I'm just going to kind of describe our experimental setup by walking you through, at first, just some qualitative examples. So essentially we're going to take two characters, or two glyphs from a font that we've never seen before, pass them to our models, and ask them to reconstruct the remaining characters that they didn't observe. And I'm going to zoom in on just one of these in particular. You see that nearest neighbors, which is kind of on the far right, is producing something which is definitely a font, like it's realistic looking, but it doesn't really have any stylistic properties in common with the examples that we showed it. GlyphNet does a little bit better because it gets the overall silhouette right, but our model kind of does the best in terms of getting the most stylistic properties like that heavy drop shadow and kind of approximating the floral pattern that's on the lettering. So since that's just qualitative, now we want to kind of quantify those differences. And we're going to do that by looking at the L2 distance between the reconstructions that these models output and the true gold fonts that were kind of masked from them. And we're going to do this for several random numbers of observed characters. So for, say, 8 randomly selected characters for each font, we ask the model to reconstruct the missing 18, for 4 with 22, and so on and so forth. And we see that our model kind of has the best L2 score, the lowest L2 score, followed by nearest neighbors, and then by GlyphNet. And what we see is that as we reduce the number of observations in each column, the models start doing worse and worse until you're down to just one observation, with GlyphNet kind of suffering the most. And one thing that you might notice here is that nearest neighbors is actually beating the GAN, which is kind of unusual, but it makes sense when you think about the underlying structure of our data. So fonts data tends to have some pretty strong modes in it. So for example, there's a whole lot of fonts that look similar to Times New Roman, there's a lot of fonts that look similar to Arial, and nearest neighbors is really good at exploiting this property. But in order to better measure how our models are generalizing to completely new fonts that don't look like things that they've seen before, we also perform an evaluation on a subset of our test data, which represents the 10% of fonts that have the maximal L2 distance from their next nearest neighbor in the training set. So these are like the most unique fonts in our test set. And we see that on these, the baselines have kind of flipped now. So we're still doing best, but nearest neighbors is doing quite poorly because it's not really good at finding an example in training that matches these completely novel fonts. But because GlyphNet suffers a lot from having few observations, by the time you get down to only one character, those have kind of flipped back again. And since L2 isn't really a great metric when you're talking about like image reconstructions, we also did some human evaluation. So here we asked Turkers to sort of rank our model against GlyphNet according to realism and then also stylistic fidelity. And we see that generally they agree that our model kind of does the best job on both of those criteria. And fortunately, there's a good amount of inter-annotator agreement on that. So one final qualitative thing that we can do, which is pretty fun, is we can use the fact that we've learned this sort of smooth manifold over style to generate novel fonts that kind of lie in between examples that humans have actually designed. So for example, if we have like a light font and a bold font, we can pass them through our encoder network to get points in our manifold, and then we can draw a line between them and interpolate at various points along the way. And what we hope is that when we pass these interpolations into our decoder, we should get outputs that to us as humans kind of make sense as lying semantically in between those two endpoints. And we see that this is in fact the case. So I'll start by returning to the example with the serifs. This is a serif and a sans serif font from the same family, and we see that we're able to kind of slowly erode those serifs away for the characters that have them, but for the ones that don't, like the O, it leaves those untouched. And then we see something similar with italicization, where here it's able to apply a gradual amount of shearing to all of the characters equally. As well as with boldness, where we can show an actual light font and an actual bold font, and now we can kind of create these new fonts that have like in-between boldness of various different amounts. So to summarize this work, essentially we've here introduced a deep generative model which factorizes glyphs into these disentangled representations of the style of the font and the structure of the underlying character. And we've leveraged amortized inference in order to let us cast this reconstruction task as one specifically of matrix completion. And one thing that's really cool about this is that most of this model so far is not really that specific to fonts as a task, or even just vision. So we do believe that this is the sort of approach that could potentially be extended to other domains, as long as you have your data coming in this format where you have sort of lightly supervised alignment where you know which elements correspond to the same column, which elements correspond to the same row. We believe that this is an approach that could potentially be useful there. So that's all I have. Thank you very much for listening.
Well, thanks for the fun talk. It's totally worth the waiting. And I would like to ask, actually, have you ever tried to generate ambigrams using those methods? You know, when you flip the word.
Oh, were you?
So
no, we haven't. That's an interesting idea.
That could be a very fun application, yeah.
Yeah, so one thing that we are working on right now, which could potentially lead us there, is, you know, we talked earlier about how we have these like latent variables for the font and how the characters were just parameters that we were learning. There's some work we're doing right now on actually making them both kind of latent manifolds, where we'd be able to interpolate between characters and things like that. Yeah, so imagine the E's being circles also. That's something we're working on right now, but it could potentially lead us to being able to do something like that.
Okay, let's send the speaker again.